Hi, I'm Vitaly Feldman, and I'm going to talk about the role of memorization in learning. More specifically, I would like to show that the properties of the natural data distributions require that we revisit our ideas about generalization in machine learning. Oops, almost forgot my mask. So the goal of this work is to explain the well-known empirical phenomenon that deep learning algorithms eagerly memorize training data labels. What I mean by this is that when trained on common image and text classification datasets, these algorithms fit the training data very well, often achieving training error that is zero or close to it. At the same time, their test error, which measures the generalization error, is much higher, often in the range between 10 and 30%. What this means is that the data distribution has a large fraction of points which the learning algorithm cannot classify accurately. This fraction typically includes a significant fraction of outliers and mislabeled examples. So naturally, these hard-to-classify points are also present in the training dataset, but the learning algorithm fits their labels anyway. And if you think about it, the only way to fit the labels that the learning algorithm cannot predict is to effectively memorize them. A more extreme version of this eagerness to memorize labels was shown in the well-known experiments of Zhang and others. In one of their experiments, they trained a deep learning algorithm based on the inception network on the ImageNet dataset labeled completely randomly. This dataset is quite large. It contains 1 million images and has 1,000 classes. But the model that was produced in this experiment fit all but 9% of those random labels. Of course, nothing useful can be learned from random labels, so the test error of the model was essentially 100%. Clearly, fitting completely random labels requires memorizing them. Let me now define the notion of label memorization formally. For a dataset S that consists of n labeled examples, an index I of an example, and a learning algorithm A, we measure the memorization of the ith example as the difference between two terms. The first term measures how well the algorithm fits the ith example. The probability in this term is necessary since most learning algorithms are randomized. The second term measures how well the learning algorithm predicts the label of the ith example when the example is removed from the dataset. In other words, how hard the label is to predict without observing it. So this definition captures the intuition that fitting an example that the algorithm cannot predict requires memorization. Informally, we'll say that an example is memorized if its memorization value is larger than some fixed positive constant, for example, 1/2. This notion has a nice property that it can be directly related to the difference between the training and test errors. Specifically, for any data distribution P over labeled examples, and a dataset S drawn IID from this distribution, the expectation of the average memorization value for all the examples is basically equal to the expected difference between the generalization error of the model output by the algorithm on the data distribution and the empirical error of this model on the dataset S. This difference is referred to as the generalization gap and corresponds to the difference between the training and test errors. So if we observe that this value is large, such as say 30%, then we can conclude that the learning algorithm memorized a significant fraction of labels. Let me now briefly discuss the relationship between label memorization and existing theories of generalization. At a high level, the standard approach to understanding of the generalization error starts by decomposing the generalization error into the empirical error and the generalization gap. The empirical error is easy to measure and optimize, but of course we cannot directly evaluate the generalization gap. Instead, this gap is upper bounded by its worst case value for this algorithm, which in turn is upper bounded using notions such as model complexity or stability. Perhaps the most famous result of this type is the classical VC dimension that guarantees that for all binary classifiers from some class of functions f, the gap is upper bounded by the order of VC dimension divided by the square root of n. So this approach relies on some kind of proxy for the generalization gap, And the learning algorithm based on this approach is supposed to be minimizing the sum of the empirical error and the value of the proxy. Now, it is intuitively not hard to see that for every label that is memorized, the algorithm needs to increase the complexity of the model or whatever the proxy it uses. In the worst case, the memorized label could be incorrect, or the example could be a useless outlier. So the worst case value of this generalization gap will increase by at least as much as we gain in the empirical error. In fact, for most proxies, the increase will actually be much larger. For example, for the VC dimension, the increase is on the order of 1 over square root of n, whereas we gain only 1 over n in the empirical error. So at best, this approach cannot explain the label memorization, but actually in most cases, it cannot give a meaningful generalization bound for an algorithm that memorizes a significant fraction of label. Effectively, it suggests that label memorization is the opposite of learning. A related issue with standard theoretical analysis is that they also focus on the setting where the generalization gap is close to 0. In this setting, being a constant factor off is not a big deal, but in practice, this gap is so large that analyses that are a factor 2 off are basically useless. These issues with standard analysis of generalization are now recognized by the experts, but still pretty much all the existing theoretical work on generalization of deep neural networks relies on this approach. As a result, these works cannot explain label memorization. One line of research that tries to address the limitations of the standard approach is the work on understanding of interpolating algorithms. Here, interpolation means that the learning algorithm fits all the training labels perfectly. Such algorithms are actually not new. The one nearest neighbor algorithm, which is one of the first learning algorithms to be studied, is an interpolating algorithm. And some generalization guarantees for the nearest neighbor algorithm were proved more than 50 years ago by Cover and Hart. As I mentioned, neural networks tend to have small training error and actually do interpolate the training dataset in many cases. So this has motivated quite a bit of research on interpolating algorithms in the last couple of years. At a high level, these works show that in some cases, specific interpolating algorithms have asymptotically optimal generalization guarantees. But for the problems that are studied in these works, non-interpolating algorithms and standard generalization analysis can also be used to obtain such optimal generalization bounds. So these works show that interpolation can sometimes be harmless, but they do not explain why interpolation should be used in the first place. Let me also point out that label memorization happens even without interpolation. For example, in the experiment of Zhang and others that I mentioned, the training error was just 9%, even though there was clearly a lot of label memorization. Let me now describe the intuition on which my explanation and theory for these phenomena are based. I'll do this using actual example from the CFAR10 dataset and results from my experimental work with Chiyuan Zhang, which I'll tell you a bit more about later. Let's look at these 4 examples of the track class from the training dataset. What's special about them is none of those examples would be classified as a track if they were to be removed from the dataset. So they are hard to classify, and as we discussed, would need to be memorized to fit. This is also not surprising since these are clearly not typical tracks and are probably very different from all the other examples of the track. So the question is whether it is worth memorizing these examples. The answer certainly wasn't clear to me a priori. But in a work with Chiyuan Zhang, we were able to measure usefulness of examples, and it turns out that memorizing the first example is useful. If we were to remove this example from the dataset, it would significantly decrease the accuracy when classifying this example on the right from the test set. On the other hand, and well, it's not a huge surprise, the second example does not improve accuracy on tracks, so it's effectively useless. The third example is actually useful since it improves accuracy on the example on the right from the test set. And the fourth example again appears to be useless. So we see that as a whole, memorization is useful. But what is even more interesting is that without access to fresh samples from the distribution, it might be impossible to tell which of those examples will turn out to be useful. Basically, they're all very different from all the other examples of the truck. So in order to get the benefit of memorizing the useful examples, the learning algorithm also needs to memorize the useless ones. And this is exactly why the resulting model ends up having such a large generalization gap. They memorize a lot of useless examples just to make sure that they also get the benefits from the useful ones. This can also be seen in a nutshell, the reason why our theories of generalization fail in this case. They're based on bounds that estimate the worst case result of memorization, and in the worst case, memorization is actually useless. Let me now tell you where I think these hard and atypical examples come from. And for this, my main observation is that natural data distributions are not homogeneous, like our favorite Gaussian distribution. They're better thought of as consisting of numerous subpopulations or clusters that are quite different from each other. For example, the class of birds in the CIFAR-10 dataset contains images from hundreds of bird species taken from a variety of angles at different magnification and backgrounds. These subpopulations are very different from each other. So a learning algorithm that only has 5,000 examples of birds may be unable to accurately classify as a population without observing any representatives from it. And because there are so many subpopulations, some of those subpopulations will have frequency on the order of 1/n. These subpopulations are useful, but the dataset will usually include just a single example from each of those subpopulations. Examples from extremely rare subpopulations, or outliers, also have just one example per subpopulation. So for subpopulations with just one representative example, it is impossible to tell whether they are useful or not. In addition, when you only have a single representative from some distinct subpopulation, it may be impossible for the algorithm to distinguish a correct label from a noisy one. So my point is that useful examples from subpopulations with frequency on the order of 1/n may be indistinguishable from much less frequent and useless outliers, and the algorithm may be unable to tell if the label of those examples is correct. So the only remaining question now is whether these low-frequency subpopulations are important for achieving high accuracy, or perhaps can be just ignored. The answer clearly depends on the distribution of frequencies of the subpopulations. Informally, it is well known to many practitioners that natural data is long-tailed. And what they mean by this is that rare and atypical examples make up a significant fraction of the distribution. There are also several works that give empirical evidence of such long-tail behavior. For example, Zhu and others use the additional annotations available in the SUN Vision dataset to plot the number of examples for every visibility pattern of the classified object. Here are some plots from their paper for the bus and person classes. In addition to frequency plot, they also show some examples of the most common visibility pattern, medium frequency, and also one of the rare ones. In the top right corner, they give the plot of the number of examples as a function of the frequency rank on the log-log scale. As you can see, this plot is close to linear, with the slope being -1. The -1 slope corresponds exactly to the zip distribution, in which the frequency of the kth most frequent element is proportional to 1/k. This is the prototypical long-tail distribution, famously followed by the frequencies of words in many languages. Now, for this distribution, if the total number of elements t is larger than the number of samples n, then the total weight of all the frequencies on the order of 1/n is roughly 1/log t. So as you can see, for t in a reasonable range, the fraction of the data distribution made up by frequencies on the order of 1/n is significant and therefore important for achieving high accuracy when learning. I hope that this high-level outline makes sense. In case you are starting to get worried about the absence of theorems, let me show how to formalize these ideas. For this purpose, I'll start with a very simple model to isolate the phenomenon we're interested in from other modeling issues. In our model, we'll have a discrete domain X of size T. We'll use D to denote the marginal distribution over X, and we'll assume that there is some true labeling function F that labels the point. We'll use P to denote the data distribution that is obtained by drawing a point from distribution D and labeling it by function F. The main new element of our model is that instead of assuming that nothing is known about the distribution D, we'll assume that frequencies of elements in X have a certain shape. In other words, we'll have some prior distribution pi over frequencies. In addition, we'll assume that for every point X in the domain, the only information that the algorithm has about the true frequency of X comes from the number of times X was observed in the dataset. To express this, we'll define the following way to generate a marginal distribution. For every point X in our domain, we'll pick a frequency randomly and independently from the prior over frequencies. And since we want this to be a distribution, we'll normalize it to 1. We'll be focusing on the expected generalization error of a learning algorithm over a random choice of the marginal distribution D according to the process that we have just described, and also a random choice of a function F from some distribution over labeling functions capital F. The expectation over the choice of functions is not important and can be replaced with the worst case error, but it's a bit easier to just plug everything into a single expectation. Also, the expectation over the choice of D can be replaced with a high probability bound, since the quantities we consider are well concentrated. But we'll focus on the expectation to keep it simple. I can now state a special case of the main result of this work. Informally, it shows that any algorithm that does not fit the entire dataset will be suboptimal and quantifies this suboptimality. The interesting part is that all examples need to be fit, even outliers that are not useful for generalization. More formally, the error of any learning algorithm is at least the optimal error, which is just the minimum over all algorithms of the error, plus the suboptimality term, which is some factor tau, times the expectation over the same random variables of the number of examples occurring once in the dataset S, but not fit by the algorithm A. So anytime an algorithm does not fit an example, it becomes suboptimal, and the conversion factor tau is defined as follows. It's not so important what it is. It's just worth noting that it only depends on the frequency prior pi and the number of examples n. In addition, it is very easy to estimate. In particular, we show that this factor tau is lower bounded by the total weight of all the frequencies on the order of 1 over n divided by n, where n is just, this division is just a normalizing factor. Also note that the distribution over labeling functions f does not matter in this result at all, but as you'll see in a moment, it will play a role once we start talking about memorization. To see this, let's start by briefly recalling the definition of memorization. It measures the difference in the classification accuracy on an example between the case when the example is included in the dataset and the case when it is excluded from the dataset. Now, it's not hard to see that the expected accuracy of an algorithm on an example that was excluded is equal to the expected true accuracy of the algorithm on the distribution. This means that if the learning problem is sufficiently hard, then many examples cannot be classified accurately when they're removed from the dataset. By our definition, to fit such examples, we need to memorize them. Now, by combining this with the theorem from the previous slide, we obtain that memorization is necessary for getting close to optimal accuracy. Let me also briefly mention that for these results, I'm going to ignore label noise, since I think that the key phenomenon here is really about the long tail of frequencies. But it's not hard to add noise into the model and show that memorization of some of the labels can be necessary even in the presence of noise. So far, I've been talking about the discrete domain and frequencies of individual points. Of course, in most learning problems, the domain is high dimensional and the probability of each individual point is negligible. In such domains, fitting or memorizing labels of individual points does not make any difference, so the results we have discussed cannot be applied directly. To extend the model and results to this setting, we'll view the marginal distribution as a mixture of distributions, each representing a subpopulation. More formally, let M1 through Mt be T distribution over X with disjoint supports. Each of them represents a subpopulation. We'll also assume that the labeling function f is constant over subpopulations, since each subpopulation is a subpopulation of some class. Next, we'll define a process that generates a marginal distribution in a very similar way. For every subpopulation, we pick a frequency from the prior distribution over frequencies randomly and independently, and then normalize to 1. The marginal distribution is defined as the mixture distribution of the subpopulations with the chosen normalized frequencies. And as before, we'll be interested in minimizing the expected generalization error of a learning algorithm. We now define a condition on learning algorithms, referred to as lambda subpopulation coupling, that we need to extend our main result to this setting. The condition requires that for every dataset and any point in the dataset that is the only representative of some subpopulation Mk, the prediction of the algorithm on that point is close to the distribution of the predictions on the entire subpopulation Mk. Here, close means having total variation distance of at most 1 minus lambda. Basically, if the algorithm observes only a single point from a subpopulation, then its classification of the point is correlated with the classification of that entire subpopulation. For algorithms satisfying this condition, we get essentially the same result as before. The only thing that changes is that the excess error is now multiplied by the strength of the correlation lambda. It might not be immediately obvious why this coupling definition makes sense, but actually it's not hard to see that for an algorithm like the nearest neighbor classifier, the first representative of a cluster will have a significant effect on the way the cluster is classified. In the paper, I also showed that this property is satisfied by the large margin linear classifiers in the over-parameterized regime. That's all that I wanted to say about theory. Let me briefly mention that in a joint work with Chiyuan Zhang, we were able to validate these ideas empirically. Our results are based on a way to estimate the memorization value of each training example and also estimate the influence that the inclusion of each training example has on the accuracy at each test example. This allowed us to find many pairs of examples where each pair consists of one training example and one test example, which have the following property. The training example in the pair is memorized, and it also significantly increases the accuracy on the test example in the pair. Here are some of the pairs we found in the ImageNet dataset, and also some of the pairs from the CFAR 100 dataset. As you can see, these are atypical examples of their class, and at the same time, they're visually similar to each other. This is exactly what we model as the subpopulations in the long tail. Overall, the test examples in these pairs make up a significant fraction of the entire test set. This shows that it is important to classify such rare subpopulations accurately. You can find more details in the paper that we posted recently. To summarize, this work shows that label memorization is necessary for achieving close to optimal generalization whenever the data distribution is long-tailed. This result is not specific to deep learning and suggests that memorization is an inherent part of learning more generally. In terms of future work, I think that one of the most important problems in learning theory is finding more faithful models of data. And I believe that modeling of the long tail is crucial for making sure that the model captures natural data distribution. Another important direction for future work is understanding the implications of these results for privacy-preserving machine learning. A couple of connections to privacy are already discussed in the paper, but many additional questions remain. That's all, folks. Thank you, and I'm looking forward to your comments and questions during the online session.